All right, so in this video, let's talk about decimal to binary conversion. So there are actually four types of number system. So these are the binary system or base 2, the octal number system or base 8, decimal number system or base 10, and then the hexadecimal number system or base 16. Which today, let's talk about how to convert decimal to binary number system. So what are these? For example, we have 5,621. So this is called decimal because if we can raise, or if we raise 10 raised to 0, 10 raised to 1, and so on until we reach the first digit from first to right and get the sum of their products, we will still go back to our given number. So in this case, we have 1 times 10 raised to 0. We also have 2 times 10 raised to 1, 6 times 10 raised to 2, and the last is 5 times 10 raised to 3, which in this case, we know that any number raised to 0 is 1. So this 1 times 1 is 1. In this case, we have 2 times 10 is 20. In this case, we have 6 times 100, which is 600. And the last one is 5 times 1,000, which is 5,000. And to add all of these products, we can still get 5,621, which is our given number. Okay. Now next is what are binary number system. So this system is also known as base 2. The values of the positions are calculated by taking 2 to some power. Why? Because we only use 2 digits, the 0 and 1. Examples, we have this 11001010 or 111111 or all zeros. Okay, so any numbers consisting of only 1 and 0, that number is called binary. Okay, so now let's jump into converting decimal to binary number system. For example, we have this convert 67 to its binary equivalent. So it is base 10, right? So therefore, you can also write this as 67 base 10. So how to convert? So first thing here is we only need to do division by 2 repeatedly. You get the quotient and then the remainders. So in this case, we have, so 67 by 2, that's going to be 33, remainder 1. And then let's take 33 and by 2 again. That would give us the quotient of 16. And again, we have remainder 1. And again, we have 16 by 2, that's 8. And then we have remainder 0. And again, 8 by 2, that's going to be 4. Remainder 0 again. 4 by 2, that's also 2 with no remainder again. And then we also have 2 by 2, that's 1. And then again, no remainder or 0 remainder. And the last one is 1 by 2, that's going to be 0, remainder 1. In this case, we can stop now because we already have the quotient of 0. And again, you only stop if you now get the quotient of 0. Now, the remainders of these quotients, okay, this would now serve as your binary equivalent. But take note that you would have to take it upward or to read it upward to get its binary equivalent. So in this case, we have 1, 0, 0, 0, 0, 1, 1, or this case, this thing here. Okay, so therefore, the binary equivalent of 67 is 1, 0, 0, 0, 0, 1, 1, and then you put base 2 since binary is base 2. Okay, so in this case, converting 294 base 10 to binary. So again, the same process. We divide by 2 repeatedly. So we have here 294 by 2. That's going to be 147 with remainder 0. And again, you take the 147 by 2 again. That's 73. And again, get its remainder. And that would leave us with one remainder. And again, we have 73 by 2, that's 36, one remainder. 36 by 2, that's 18, with no remainder. And again, 18 by 2, 9 by 2, 4 by 2, and so on until you will reach the quotient of 0. And then just get the remainder. And again, you read it upward. So in this case, we have 1, 0, 0, 1, 0, 0, 1, 1, and 0. That would be the equivalent binary of 294 base 10. Okay, thank you and keep exploring the numbers.